let's continue. Now that we're all back. Okay, remember those name sheets. Will you bring them up if you don't mind? I'm gonna get you some nicer ones with a Sharpie, and we'll write your names on those maybe by next week. I also want you to take the opportunity now to self-select into groups, at least 3 up to 4 groups, okay? Eventually, you're going to come up with a group name. I'll talk about that on Tuesday. But I want you at least to start kind of self-selecting into groups, at least 3 groups, up to 5, 4, you know, like here you guys together. Over here, you can split in 2, over there. Yep, you can combine together, look behind you, next to you, get to know your neighbor, ask their name, you know, and yeah, get to know them. They're going to be your colleagues in chemical engineering. Yep. Yeah, so now eventually your groups are going to have names, okay? And I'm okay with funny names. So, you know, we leave that up to your imagination. I'll send you a notice on Canvas for you to come up with a bunch of names, and then we'll print out, laminate them, and you'll have your group names. And I'll be working with the group, sometimes with the individuals, but most of the time with the group. You get a chance to talk to each other and reason about things as we do some activities. Sometimes time is short. We don't have much time to do like full onboard activities. So, you know, those will be limited to a very quick discussion. But to the extent possible, at least you get a chance to know your neighbor and, you know, get to know them, get to know more people in the department. Okay. This course, if you look at the syllabus, it is divided into 3 parts. I should remember because I put those together, but I'm buffering right now. So part 1 is about solving algebraic equations. Part 1, we're going to learn how to solve ax equal b, which you know, x equal b over a. We're going to take that and learn how to do it on a system of ax equal b and so on, a system of equations, not just one variable, one unknown. You'll have 2, 3, 10, 100, or 1,000 unknowns, or 1,000,000 unknowns. Okay, so linear systems of equations, they're algebraic. We will also learn how to do nonlinear equations. Those are equations that are not linear. I'll explain that later. But also systems of nonlinear equations. So part 1 is all about algebraic equations. Part 2, now there's a reason for this insanity that we do linear systems and nonlinear systems at the beginning, because everything else in the course is going to be we're going to turn it into a system of linear equations or nonlinear equations. And then with nonlinear equations, we're going to turn them into linear equations. Okay, it all goes back to linear systems of equations. That's why linear algebra is a field by itself. It's very fundamental in math and science. So part 2 will be on data fitting, data analysis. So we're going to take data. We're going to learn how to interpolate it, how to sum it up, integrate it, and maybe do some regression analysis on it. If not, I'm going to catch you in the spring for statistics, so you're stuck with me. Okay? So I'll catch you in statistics, and I'll teach you that in statistics. Okay? But you'll be ready to do it the right way. Okay? If we do it this year here, it's great. If not, we're going to definitely revisit it in statistics. So that part is data fitting, because we're trying to set you up for data to be data scientists, really, to learn how to work with data. Without statistics, without programming, without numerical methods, you cannot do data analysis. The last part of the course, so we did algebraic equations, data analysis, kind of doesn't fit with the theme if you think about it, but it is important for anything that has to do with data, which is going to turn into part 3. So in part 1, we solved algebraic equations. In part 3, we're going to solve differential equations. There's algebraic equations where you're directly relating the value of the variable to something else. With differential equations, you're relating the rates of change of those variables to other things. Okay? So we learn how to solve differential equations. You're going to need data analysis to interpret the results of your differential equation solution. So, and at the end of the semester, I reserve one lecture. My colleague and friend, Professor Dr. Camilla Steibel from Europe, she will give a lecture on machine learning, artificial neural networks. So we'll get you kind of exposed to that a little bit so that we can use it later. Okay. Now, there is one chapter that is fundamental to all of those other parts and doesn't belong in a part. It doesn't belong anywhere. So it stands on its own, and that's why I don't call it a part. It's just a chapter, and it's called error analysis. Okay? So we cannot talk about anything in science and engineering without talking about the errors we're committing. We're making mistakes because we're making approximations. I think there is, this very objective truth answer. All the tools we have are approximating that answer, whether because we cannot measure things correctly, because of quantum mechanical effects and precision issues. Try to measure the position of something, then you mess up its momentum. You try to measure the momentum, you mess up its position. So there's always uncertainty. All right, let's start with this. And my apologies again for the washout board. Let's see. Turn this on, so hopefully you can hear well.
It's the 4th of June, 1996, and the European Space Agency is launching its brand new Ariane 5 rocket for the first time. This is a big deal. The Ariane 5 is designed to carry large, expensive scientific and commercial payloads into space and heralds a brand new era for the ESA. A decade of design and testing and billions of euros have led up to this day. The Ariane 5 rocket carries no astronauts. The first payload is 4 very expensive scientific satellites to be delivered into orbit. Things start well. The rocket clears the tower and accelerates smoothly. And then the rocket abruptly changes direction, starts to break apart, and suddenly explodes. Less than a minute after launch, huge chunks and glowing fragments of Ariane Flight 501 rain down over the launch area. A shocking disaster for Ariane and the ESA. The cause? A simple, utterly avoidable coding bug. Okay, here's what happened. The Ariane 5 leaves the launch pad and accelerates smoothly into the sky, following its predetermined path towards space. Inside, the onboard guidance system is constantly tracking the rocket's trajectory and sending the data over to the main flight computer. To do so, the guidance system converts the velocity readings from 64-bit floating point to 16-bit integer. Okay, stop for a second, and let's think about what that actually means. Computers store numbers in a variety of ways. Consider 4-bit integers. 4 bits can represent anything from 0 to 15. But if you want to represent the number 16, well, there just aren't enough bits, are there? 16 is too big. You need more bits to store bigger integers. With 16 bits, you can store anything from 0 to 65,535. Or, if you throw in a sign, then 16-bit signed integers cover everything from minus 32,768 to positive 32,767. But anything bigger than that, and again, you've run out of bits. Floating point numbers are stored a bit differently. They're stored as a decimal, or significand, and an exponent. The details aren't really important here. All you need to know is that 64-bit floating point can store much larger numbers than can fit into a 16-bit integer. So converting between them can be tricky when the integer runs out of bits. So what does happen when you run out of bits? Well, if you're using 16-bit signed integers, the conversion will just wrap around to the beginning again. But whatever the details, you're definitely getting the wrong answer. This is known as an integer overflow. Right, so back to our rocket. The guidance system reads the horizontal velocity data of the rocket as 64-bit floating point and tries to convert that into a 16-bit integer to send over to the main flight computer. But at that moment, the velocity reading is actually larger than the largest possible 16-bit integer. The system tries to do the conversion and fails. Now, a clever system would have some procedure built in that says, hang on, we're piloting a rocket here. I need to say something sensible to the main computer. It would have some overflow error handling code. But in this case, guidance system code isn't very clever. So it just sends an error message in place of the velocity data and promptly shuts down. Fortunately, there's a backup guidance system in case the primary module breaks down. Unfortunately, it's running the same code, so it does the same code, gets the same code, and crashes for the same reason. The main computer receives the error message, and because there's no handling code built in, the computer interprets the message as real navigational data and immediately freaks out. The velocity reading is off the charts, indicating that the rocket is dangerous, impossibly off course. So the flight computer does what it's designed to do. It fires up the boosters and drags the rocket around in an attempt to rescue itself from a non-existent disaster. This puts the fuselage under incredible aerodynamic strain, which starts tearing the rocket apart. Detecting that things are now really going badly, the computer calls it a day and triggers the built-in self-destruct mechanism. So, what was the ultimate cause of this incredibly expensive, very short, and ultimately catastrophic rocket flight? A simple line of code, converting a floating point to an integer that led to an overflow passed without warning to the main computer, which was interpreted as real, if wildly inaccurate, data. The flight software had been used previously with no problems on many flights of the smaller Ariane 4 rockets, but the Ariane 5 was designed to fly faster than anyone planned for when the software was originally written, and the higher velocity led to the overflow error, a flaw that should have been found. It just never came up. Want to know the worst bit? That buggy bit of code wasn't even necessary during flight. It was part of the launch pad alignment process and shouldn't have been running after liftoff. But sometimes, a small glitch somewhere causes a launch to be delayed by a few seconds. So to save having to reset the system, the original programmers decided to keep that bit of code running for 40 seconds after the scheduled liftoff time.
Ah. That's too bad. Well, that's one type of error that we encountered in numerical methods. Luckily, modern computers, we don't have to worry about that. In your homework too, you're going to solve a problem similar to this one, because that's not the only disaster that's happened because of these translation errors. There's an issue with the Canada Stock Exchange where they messed up some round off, and some people got ultra rich overnight. Some others got they lost all their money, but it was a glitch in this kind of stuff. So we're going to talk a lot about this as we go through the course and try to appease your mind a little bit, but also, tell you that this is serious stuff. We have to be careful about what we do as engineers and what codes we write. Throughout the course, you're going to see, if I'm consistent across the slides, you're going to see about these 4 types of boxes scattered in the slides. A blue box is going to refer to an activity. So you see a blue box, there's like an activity that I'm asking you to do. It's going to be a group activity or individual, I'll tell you. A slightly greenish, whatever that color is a coding activity. A gray box is a definition that you have to memorize or just retain. Code snippets are shown in that one. There's also a yellow box for a problem that I'm doing in class for you or some important statement. And then, an example that we do in class, which is green. OK. Our first activity as a group is going to be, what is x minus 1? Just in your mind or on your paper. Talk. Is there any restrictions on x? It is not a trick question. What is the mathematical answer for x minus 1? All right, let's see. Do we have any answers? 0.
We got
1. 1. OK. Who else got 1? OK. This is not a democracy, so no matter what your vote is, it's not going to, if it agrees with the answer, it's not going to be the answer, right? But yeah, it's 1. I agree. Even if x approaches infinity, what you do, you say in the limit that x approaches infinity, you have to manage the variable symbolically before you apply x equal infinity there, right? And then indeed, it is exactly 1 for any value of x. OK. Our first coding activity is going to be implementing this formula simply in a code cell and setting the value of x equal 10 to the power 16. Okay? If you have your Jupyter notebooks open them up. If not, that's OK. I'm gonna do that for you. And hopefully, we'll have that ready on Tuesday. All right. I'm going to go into my activities and I'm going to create a new. OK, so if you're looking at, OK, so this is what my Jupyter notebook folder looks like. OK, I got a bunch of things. And you go and say, create new Python notebook. That's it. It created a new Python notebook. The first thing I'm going to do is coding in class coding activity in class coding activity x minus 1. OK, whatever you want to call it. OK. Now, in Jupyter notebooks, you can mix, I said, text and code together. So the first thing you want to do is when you look at this, gives you this cell, it tells you in. It's seeking input from you. OK? So now you can convert a cell between text or code. You simply go here, cell, and you say cell type. I want it to be Markdown. Markdown is simply text. It's just a type of text. It's called Markdown. Forget what that means. It's just simply a type of text that allows you to write math and stuff. So what I'm going to do, I'm going to convert this cell to Markdown. I'm going to say, OK, so coding. If you've been on forums online, you probably are familiar with some of this syntax. Coding activity class. OK. And then if I press Shift Enter, look at that. Turns it into a nice kind of header. Now this cell is also, it automatically goes into a new cell and turns it into a code cell. It's showing this in. It's blue. I need to convert that also into a Markdown cell. You can go back here and say cell type. But if you notice here, it has these little squares over here, Y and M. Those are shortcuts to convert a cell without having to go through the menu. So if I go on the cell here, if I press M, look at that. It turns it into now this is a text cell. It's a text cell. I can go back on it, and if I press Y, it converts it into a coding cell. Now this is a coding cell. Okay? So I need this to be a text cell. I'm going to press M. It's going to be a text cell. And what we are asked to compute the value of x minus 1, okay, with x equal 1e to the 16. Okay? Okay, so this is text, right? This is acceptable, but I will ask you to do better. I'll show you in a second. All right, so let's first do this. X is 1e to the 16, right? To make it better, I can put 1.0e to the 16. I just simply declared a variable called x, and I stored the value 1e to the 16 in it. OK, so next I need to do x minus 1, exactly like the math says. And I'm going to store this in a result variable. Result is equal. OK, it's going to do it. All right, what is result? Did you print it? OK, what did we get there? 0. Whoa. Did you get, who else got 0? Right? What the heck is going on? Print. Result. Print. Result. It's 0. It's not 1. Because in the process of doing this calculation, that extra 1 was outside the bound of what the computer can handle with 1e to the power 16. So even with modern computers, such a large number, okay, this one couldn't even make it when it was adding the bits together, okay? All right, so go back to the slides. We'll do more of those stuff later. So this is the result, will be 0. Okay. All right, so don't trust your numerical implementations just blindly, okay? You need to be careful to understand what you're doing. Let's begin. Welcome back to the second week of your happy life, I hope, here with numerical methods. I want to make a couple of announcements related to the homework and the exam, and as you go through, the rules and expectations for this class. So I want you to imagine that I tell you, each one of you, you get a chance to go to this parking lot that has a lot of new cars in it, Lamborghinis, Ferraris, all sorts of fancy cars, Mustangs and stuff. And I tell you, I'm going to gift you a car. I am going to choose it for you. Versus, I'm going to take you to this parking lot. It's a well-defined parking lot, and the cars are in there. It's the same cars. But then I tell you, you get to choose whatever car you want. Which would you rather take? Would you take the option of me choosing the car for you, or you choosing the car that you like, the color you want, the whatever you like in the car? Which one would you choose? Who's for option 1? Okay, who's for option 2? Okay, yes, of course. Okay. Still, human nature is still good and going. Okay, so why did I make this analogy? And I give this analogy to my PhD students. They come in and they ask me, what research project am I going to be working on? I'm like, well, we're going to be working in this area. We have these questions we want to ask, but it's up to you to figure it out. You choose what you want to discover and make a difference in this area. And when I give them the car analogy, they're like, yeah, now that makes sense. If you prescribe the research for us, for me, there's no opportunity for learning and growth because I'm prescribing the research and I'm prescribing the methodologies, et cetera. Instead, if I act as a guardrail and a sanity check, a sounding board, and have the students, the PhD researcher, do the work, figure it out themselves, they come out smarter, richer experience, more independent, and more capable of leading on their own. And this is what I want from you, okay? You're no longer in high school where Mrs. Butterfield comes and tells you, you do question 1A and write it in this kind of font or whatever. Like, hey, here's the homework assignment, okay? So you see what I'm getting to. Here's the homework assignment. These are the boundary conditions for you. You have to submit a Jupyter notebook. You have to, work on it a little bit. But, you're not high school anymore. You're going to be engineers. You're going to be decision makers. You're going to be helping decision makers. You need to take initiative and creative work. The rest is up to you. Am I going to be upset if I see you replicate, one of the cells in the homework assignment, like creating a list, and then 15 cells after that exploring? You want to make a list adding strings and numbers and integers, trying to add lists further and it failing. I'm going to be excited to see that. Although I did not prescribe it, I would love for you to do that because I know you can do it because that's what you do when you open ChatGPT or open YouTube or you're, looking shopping. You start doing these, like the most insane research on something, and you get somewhere, right? I want you to be like that in this classroom and in all your classes, in your entire career, okay? So you see, sometimes you're frustrated when you come and ask me, is this the right way to do it? I'm like, what do you think? I don't know, I want you to be creative. I want you to express your way of seeing things. Of course, I'm going to help you stay within the guardrails of proper scientific and engineering methodologies, right? I'll tell you, yeah, this probably doesn't make sense, but explore that option. But you're going to have to go and explore it. And that's what I expect from you, okay? That's what I expect from all the homework assignments, your exams, and, reading the syllabus, for example. There's a ton of material on Canvas already. Go on the files directory. There's a lot of reading documents and stuff over there. Just go and explore it. Do not expect me or any of your teachers in the coming years is going to get worse. Okay, they're going to be like, yeah, you go figure it out, right? Because you're going to have to be independent. So there's resources there. Go explore them, look at them, come and ask me questions. Like the most joyful thing that a teacher would love to see, and put yourself in my shoes if you're ever tutoring some student, is that when the student comes and like, hey, I was looking at this, what do you think? I'm like, oh my God, come, let's have coffee together and sit down and talk about this. And we get talking and talking. So I want you to be like that. I want you to, because that is, if there's one way to success, is that, having that inquisitive mentality. So going back to the homework, yes, repeat it the way you like, repeat the assignment the way you like, but I want you to explore playing with those code words, with the syntax. If you replicate it and just replicate it, that's going to achieve something. But it's not the best thing that you're going to get out of it. I want you to try. I'm not going to I'm going to give you 100. Okay, I don't care. If I tell you I'm going to all 100 right now, right? So don't worry about that grade. Worry about your learning. Okay. Worry about your learning, especially starting with this little assignment, okay? Just go, try the code, play around with your Jupyter. And by the way, if you haven't downloaded or signed up for Jupyter Hub or whatever, you're already pretty late, okay? This train is going to get moving, and it's not going to look behind, okay? So you're going to be playing catch. If you haven't done so, you do that today, like right now, even in class right now. Okay, so that's on the homework. Exam 0 will be this Thursday. Check the announcement that I sent out. Front page of Canvas is your go-to page. Every time I make a change or an update, I check it to send an alert to you. I don't know if you get those alerts, but every time you're looking for something, go on the front page, search for a keyword or read through it. I always put the latest stuff at the bottom, like Exam 0. There's the discussion there for where you can get some material to get a refresher and what to expect on the exam, and sample exams are going to be there, etc. So it will be this Thursday in class. It's going to be an online exam on Canvas, 15 to 20 minutes. Haven't decided yet, but that's the expectation for that. Okay, with that, we'll pick up where we left off last time, and there was a discussion on errors. I showed you that video about the Ariane 5 rocket that crashed because of a silly bug in the code where they were converting some large number, floating point number, to an integer that has a limited number of significant figures. And every time the speed, which represented that floating point number, exceeded a certain value, the computer freaked out and then ended up crashing some silly bug. So this is part of the idea of errors committed in engineering, in science, and in numerical methods. In general, there are all sorts of errors, which we will discuss in a few slides. But in this class, we will be focused strictly on a few types of errors that are related only to numerical errors. In all my lectures and all my chapters or units, I will have a learning objectives for you, which will help you fine-tune your learning expectations and prepare for the exams. And it helps me actually put the slides and drive the discussion with you. So I'm hoping at the end of this chapter that you'll be able to define and calculate true error, relative true error, approximate error, relative approximate error. Those are critical errors in numerical analysis. You will find that the relative approximate error is our go-to error for most numerical methods. You'll identify when a true error and when an approximate error is needed. You'll be able to list some of the common errors encountered in numerical analysis, which are only round-off and truncation error, and identify which type of error is present in a particular calculation. So I'll give you a calculation. I'll ask you, what do you think the error is here? Is it round-off? Is it truncation, or both? You'll define the total numerical error and write Python codes for a bunch of things. We're going to go and do the Taylor series. We'll spend a couple of examples on Taylor series because they are important a little bit later in the course. And so it's an opportunity for me to introduce them a little bit and do some fancy coding in those slides. So you don't have to take pictures of the slides because the slides are already uploaded on the Canvas page. Just go up on the Canvas page. There's a PDF file there. And you can see, you can follow with me, take notes on your tablets if you like. All right, we'll start with a summary of some of the errors that we encounter and where they come from. And you know, you can dissect this list like hundreds of types of errors. But in general, for engineering practice, engineering science practice, you have modeling errors. These errors come from using an inappropriate model for the problem. Okay, so let's say you have a parachutist jumping from an airplane and going down through the air, and you use one form of a drag model or no drag model at all. So your model has no drag, so that parachute is going to keep accelerating, until they crash. Or you put a drag model and they reach a terminal velocity. So that's a modeling error. If you don't put a drag model, there's a modeling error there because then you used only Newton's laws without air resistance. You can choose one drag model over another. There's still some modeling error there, which might agree, not agree with experiment, but that's a well-understood type of error. It has strictly to do with the person who is modeling the system, which is you, the engineer. Okay. So in a way, it's a kind of a human type error. Programming errors, those are mistakes in your code. Again, those could be human errors or GPT errors or a combination thereof, and a humanoid, you augment yourself with GPT and you still make a programming error. So that's a programming error. Numerical errors, which are our main concern here, strictly restricted to errors emanating from numerical methods themselves. There's two types, round-off errors, because we have a limited representation of numbers on computers. So exactly what happened in the Ariane 5 rocket. The conversion from one number to another led to chopping of some of the significant figures, and that difference is called round-off error. You're just rounding the number. Okay, we'll talk about that in more detail later. But keep in mind that any time you add, multiply, subtract, divide, or do any one of those elementary operations on a floating point number, on a calculator, on a computer, you are committing round-off errors. There's no question. There's no question. Except for integer arithmetic. Because computers, when they're dealing with integers, there's no round-off error with integer arithmetic. Okay, like adding two integers, subtracting them, you get an exact answer. There's no round-off there. But because we're dealing in general, in all cases, with floating point numbers, you're going to get round-off errors. Okay, anytime you're working with numbers on a computer, you have round-off errors. So it's inevitable. Truncation errors are the second type of numerical error that we are concerned with. And those come from the mathematical formulation of the problem, not necessarily putting it on a computer. So when you put it on a computer, you get round-off error. But what you put on the computer generally has what we call a truncation error. The truncation error essentially means that you take a full formula that is usually mathematically exact, like an infinite summation, okay? Representing, let's say you're computing pi or the exponential, right? And there's an infinite series, right? But you cannot put an infinite number and summation, infinite loop in your code. So you have to truncate it. You say we're going to add only the first 100 terms in that series. What you left off is called the truncation error. Okay? So whatever you leave off from your exact mathematical formula is the truncation error. You take a derivative. The derivative is an exact continuous operation. But you approximate the derivative with a formula. That approximation minus the true derivative, the difference is going to be your truncation error. And we will visit all of those issues as we move on through the course. So the concept of these two concepts are going to be with us throughout the rest of the course. And we're going to look at truncation errors a lot in approximating derivatives, and when we're doing differential equations, okay? Because those become very important in those cases. Okay, now how do we measure errors? Obviously, you know, we can talk about an error as much as we like. Yes?
So with round-off errors, is that just like include not allocating enough memory to like a variable?
Not only that, not only that. Even with the most kind of biggest computers, every time you operate on floating point numbers, you're going to have truncation error. And if the number gets bigger than the memory, whatever happening in, because you cannot predict all the operations and how many digits they're going to start adding into your calculation. So there's going to be chopping off of those digits that go beyond the number of bits. And so, you know, you're going to end up with round-off errors. Yeah, anytime you do an operation of, you know, 3.5 over 17.36, you know, that's going to be a number with an infinite number of digits in it. Even if you put it on a 256-bit computer, you're not going to fit it. Anything that you leave off is going to be round off. Okay? So always round off. So it's one thing to talk about errors, and we can, you know, sit and, you know, sip our tea or whatever and talk about errors, but if you don't measure them and report them, that discussion is useless, okay? So engineers and scientists, we produce quantitative things that we report, and we can say with confidence that the error here is this much or that much. So we need to measure errors. All right, so how do we measure errors? The error, by definition, you probably know, is the difference between two things, right? Something that you think is true and something that you think is an approximation to that, right? That's kind of basic concept we know about the error in committing something, okay? The error committed in measuring something. We start by some definitions. The definition of a true error, I will also refer to that as absolute true error, is simply the difference between some true value and an approximate value. Before you start asking me about, oh, true value, what is true value? Let's go through the discussion, and all your answers will be, all your questions will be answered. All your questions, okay. So mathematically, this is defined as the difference of some true value minus approximate value. So, you know, to anchor the idea in your mind, just say you know the derivative exactly, and you have a formula to approximate the derivative. You take the difference between the true value from analytical analysis minus the numerical value. That gives you a true error. Yeah, this kind of makes sense. Often, we report the absolute value of the true error. So we put an absolute value around them because we're not really interested if the error is going to positive or negative. We're just interested in the value of that error, how big it is. Okay? So, and I refer to that as capital E with a subscript T for true. Okay. So here's your first activity for your groups, and thank you for putting your name tags out. So remember the groups that you formed last time, recongregate into those groups, and let's do this first activity. I want you to grab your tablet and pencil or pen and paper, and we're going to work on this problem together. So just give me a minute to describe it. So the first derivative of a function, this is a formula that you learned in high school to approximate the derivative. It's rise over run, right? Rise over run, okay? And it's given for any function f, some function f. The derivative is approximated as f of x plus h minus f of x over h. What is h? It's some small value. Don't worry about that. It's just some small value that the user can specify. So now for the function 2e to the half x, I want you to find the true error in evaluating f prime of 3 using these two values of h. Okay? So start by finding the true answer for f prime of 3 using your analytical formula, right? The derivative, the true derivative for this. You can use your calculator to get f prime of 3, and then evaluate the approximation and take the difference. Okay? So that's what we will be doing here. Okay? All right, take a few minutes to work on this. You can use your calculator to find the value for the derivative. So if you can't do the derivative of this function by hand, you're going to have trouble on Thursday. Remember, the true error was the difference between the true value and the approximate value. Okay? Work in groups, please. It's okay to work in groups. All right, so find the true value first, then find the approximate values and take the difference. You can work in groups. Please do. You can work together, that's okay. One of you can be a scribe, the other one. Did you find a group? Yeah, we were with them. Okay, okay. Good, good. Yeah. Yep. Yep. You got it. You got it. And then, yeah. Yeah. And then compare it to the exact f prime of 3. Right? Yeah. Right? So that gives you the true error. You need, what is the true value? It's the one you get by hand from your calculator. Okay, that's the true value. We're going to assume that's the true value. All right. Okay.
All right.
Okay. Get some numbers. Okay. Are you all working together? Yeah. Yeah, and or up front. Unless you want to hang out here. Okay. So keep plugging and chugging. Hey Devin, how are you? Okay. Yep. Yes. Yes. We stuck? A little stuck?
Oh, no, I'm just...
Okay, working them. Okay. All right. How we doing here? You got it? A little bit? Okay.
Got our approximation. Plug it in, right? Is that it?
Yeah, so for the true value of f prime, okay, so that's using h, so I don't remember the value. Yep. Say x plus h, yep, you got it. Good stuff, yep, okay. So now it's just a matter of just putting it in the calculator, right? Okay. You all are rock stars. I'm like walking around and you all know this, so I need to make these examples a little harder, right? Okay. Let's see. So can someone describe what they did? Let's pick a group. Let's see. How about your group? Since I spoke to you last, and you had it right. So can you just describe what you did?
So it
Uh-huh.
We replaced x with x plus h.
Correct? Yes?
Add it to minus fx.
Uh-huh. So you implemented this formula. In place of x, you put you put what? 3, right? Because that was x. And then for the first value of h, you put 0.5 here. For the other value, you put 0.05. And you just crunch the numbers, you got a value. And how did you get the true value? Let's see, another group. What was the true value here? Who wants to volunteer?
It's 4.48.
Okay, how did you get that?
We just took the derivative of f of x and then just plugged
Okay, and then you put in 3. So what's the derivative?
So, the derivative, just the function of it.
The true derivative, so the true value.
So it's the derivative is e to the power of 0.5 times x.
E to the 2.5 times x? 0.5 times x. Okay, that's right. So, and you put x equal 3 to get the true value. All right. So let me explain kind of what we did here. We first need to compute the true value of f prime of 3 for the function that's given to you. Okay, that function is 2e to the 0.5x. So you first compute the true derivative, and this is analytical by hand. So as best as we know, to the best of our knowledge, this is the truth. You're given the function, you can compute the exact derivative by hand. F prime of x is e to the half x. Okay, so you need to remember how you differentiate with exponentials. And then you evaluate the true value of the derivative on your calculator at x equal 3. So you put x equal 3 over there, and you get this number up to a few significant figures. So we can choose 3 or 4 significant figures are sufficient in this course from now on. All right. Now the next step, now you have the true value, okay? Now you have the true value. Now the next step is to calculate the numerical approximation, which was the formula. If it doesn't ring a bell, it's a formula you learned in high school, hopefully, rise over run. Okay, delta y over delta x, okay? That's what this is. It's the difference between the rise and the run at that point, x equal 3. Okay. So this is the formula. It's the same for any value of h. H is going to determine your run, essentially. The rise is going to be f of x plus h minus f of x. The approximate value for h equals 0.5. You simply plug in the numbers over there. F of x plus h, which is f of 3 plus 0.5, minus f of 3 over 0.5. And you know what f is? It's 2e to the half x, right? So you plug in the numbers, and you get some value for f prime approximate at 3, and you get 5.091, whatever, right? And the true value is 4.48. So the difference gives you a true error. Why we call it true? Because it's the difference between approximate and true value. Okay, great. I put an absolute value because I don't care about the sign of that error. Then you do the same thing for a different value of h, equals 0.05. So what do you expect to happen here? Yes. Yes, why? Smaller approximate value? Okay, so if you remember your, yes?
The smaller that h gets, the less error it'll get, because as the curve, as the tangent line gets smaller.
You're getting closer to the true derivative, right? So anyone wants to add something? I love this. Yes, keep it coming. No? Okay. So if you remember that formula becomes the true derivative in the limit as h equals 0. So indeed, we do expect that the error will be smaller if h is smaller. That's called the sanity check, right? So all of those theorems you heard your crazy math teacher talk about, they are actually valuable because they give you the sanity check. I understand from that theorem about the derivative limit that in the limit as h approaches 0, that f of x plus h minus f of x over h should be equal to the exact f prime. So that means if I shrink h, the error is going to shrink. So let's see. We run the numbers, etc. Indeed, our error went from 0.6 to 0.05, a factor of 10. Okay? What was the previous one? Hold on, let's see. Is 0.6 to 0.05. Yep, a factor of 10. Okay? indeed, we were able to shrink the error as we shrunk h. Okay, so it's good exercise. Okay. All right, but there's a problem with this. Okay, and some of you might have a problem with this. I'm going to answer your question, I promise you, because it's the same question I get every year. So we're going to get to that. But I will lead you to it. Now, there is a problem with this approach, and in that this error does not tell us how bad we're doing. So if I tell you the error in your approximation is 0.6, is that bad? Like, are we going to die? Or, it's great. We don't know, right? So how can you tell? How can you tell if something is worse or better? Just from the English words, it's worse than or better than something, right? So you need something to compare the error to, a relative measure, a standard to which you can compare your values to, right? So I'll give you an example. A 1-foot error in measuring, okay, before I show you this, okay. So let's say you are tasked, you're given some measuring tapes or something, and you're going to measure a 1,000-foot bridge, okay? And you come up and say, you tell us, Dr. Saad, that it's 1,000 feet, but we got 1,001 feet. One of you got 999. That 1-foot error is not a big deal. But then I come and tell you, come and measure like this, 2-feet table, and you commit an error of half a foot. You're going to tell me, this is bad, right? A 1-foot error in like measuring a 2-foot table is much more significant than a 1-foot error committed in measuring a 1,000-foot bridge, right? So 1,000 feet, it's going to dwarf that 1-foot error, okay? That 1-foot error is 1/1,000th of the bridge, right? But whereas the 1-foot error in measuring the 2-foot table is half of that table length, right? It's 50% of it. That's huge. So you see what we did? Once we measured our error relative to the thing we're measuring, we're able to say, this is good or this is bad, right? So that's what we're going to do next, okay? All right. So that's the example. So we define the relative true error, which is a more appropriate measure of error because it gives you context. It tells you how big that error is relative to this thing you're measuring. You're measuring surface temperature of the sun, which is 10,000 kelvins, right? And you commit an error of 100 K. It's nothing, right? Compared to 10,000 kelvins, right? But you're measuring the temperature in a room, 75 Fahrenheit, and you commit an error of 10 degrees, that's a big deal, right? You turn on the heater or you turn on the AC, that's a big deal, right? Okay, so we define the relative true error as simply the true error over the true value. Bridge, 1,000 feet, that's the true value. 1-foot error committed in that measurement relative to the 1,000 feet. So the relative to the true value gives us a relative true error. And we call the relative errors, we call them epsilon. So capital E is the true error. Epsilon is the relative error. T corresponds to the true value. We say this is the true error, essentially. So true value minus approximate value divided by the true value now gives you a sense of how big or good or bad the error is. And typically, we report this as a percentage because this value here is always going to be less than 1. Okay, an absolute value is going to be between 0 and 1. So it's a fraction. It's great to represent it as a percentage. Okay, so if you get a relative error of 0.1, that's a 10% error. A relative error of 0.2, that's a 20% error. And then you can say, I'm committing a 20% error. You say, oh man, this is big, 20%. It's a lot, right? Okay, so you take the absolute value, and I'll tell you, take the absolute value of the relative true error, and you multiply by 100%, and then you get the relative true error. All right, let's do this activity. A 1-meter error is committed in measuring a 100-meter bridge and a 10-meter bridge suspension. Yes, so we commit a 1 meter error. I'm like, who wrote this? Like, I wrote it, but I'm like trying to understand what I mean. Okay, so we commit a 1 meter error both in measuring the 100 meter bridge and the 10 meter suspension on that bridge. Okay, so which of these errors is worse? Okay, go. Okay. And how much can you demonstrate that with numbers? So crunch the numbers. So here you are given the true error. You're given capital ET, which is 1 meter, right? And you're given the true values. Okay, so we got an answer. I hear 0.1%. What? I hear 0.1%. Pardon me. 1% in the 100 meter one, and the second one, 10%. Okay, so we got. So what do you got? Anybody else got some numbers? So we have 1% in 1% error. It's just a general value. 1% error we got from the team here in measuring the bridge, and 10% in measuring the suspension. Do we have similar numbers? Okay. Yes, correct. Okay, I agree. So in the bridge, so here's how I would run this. True value is 100 meters, and true error is 1 meter. It's given to us, and then that gives us a 1% relative error. And for the suspension, we get a 10%. And now you can tell, this error is worse. Remember, this example is set up in a way that the error is the same value. It's 1 meter. We have the same error committed in the measuring the bridge and measuring the suspension. If you come and tell me, oh, our error is 1 meter, like, is that bad? Okay, only when you put it as a percentage, right? That gives you a sense like, yeah, 1% seems low, but 10% is pretty high. That's 10% of the suspension. So go and redo your measurements, okay? All right, good. Okay, so that's true errors. True error and relative true error, you can put absolute values on them. And this one you report it as a fraction or as a percentage. Okay. Okay, now, everything we did so far actually doesn't make sense. Because true error does not make sense. Okay, sorry about that. So why? Why? Why does true error not make sense? Simple words, yes? Okay, so I want to invert that. You're correct, okay? But let's rephrase it. So if we knew the true value, why do we need an approximate value, right? You know the true value, why do you need an approximation, right? What's the point of it? Agreed? Well, if you know the true value, like, why waste time on doing an approximate value? Well, in general, absolutely, yeah. This is correct 100% of the time. However, the concept of true error and true value is very, very useful when you are testing a new methodology that is completely new. What do you test it on? You test it on things you know the answer to, right? So you're developing a sensor that measures ozone or particulate matter or temperature. Like, how do you know that sensor is giving you the correct answer? You compare it to a system where you know the true value. So you could fill the tank with a known concentration of particulate matter, and you put the sensor, and see if it gives you back that concentration, right? So it's a very powerful concept. But it's valid and useful for what we call verification of your system. This applies experimentally, numerically, in coding. In our research, we do that 100% of the time. It's called verification. You cannot publish a paper in scientific computing without verifying your methods and making sure that they actually work as intended on systems that you know the answer to. And specifically in numerical methods, you can design theoretical problems by hand. You can design an analytical answer, such as the derivative example. Think of the rise over run formula as a formula to approximate derivatives on discrete data, where you don't know the derivative at all. You just got a bunch of points. You take the difference between 2 points and the distance. But how do you know that that formula is going to give you a derivative? You test it with a known function, right? So that's the power of that. Of course, we know how to compute the derivative of the exponential and sine and whatever. That's not the point. The point is not computing those derivatives. The point is developing the formula to approximate derivatives and using those exact values to test our formula, okay? So true error, I didn't actually waste your time. It's a very powerful concept, okay? It's a very powerful concept. So then, how do we in practice get in a measurement, a sense of the error when we don't know the true value? Because in the end, we're going to take our formulas, our sensors, our whatever, put them in systems that are completely unknown to us. We don't know the answer for those systems. We're going to take those derivatives and put them in nonlinear differential equations. We don't know the exact solutions to those at all. We can only get a numerical solution for those. So how can we assess the error in that case? So let's go through a little journey. Now, suppose you want to compute e to the 0.3. And this is AI-generated stuff, so you know it looks interesting. So you grab your calculator and you get an answer. Okay, you put it in your calculator and you get an answer. Now, the answer in that calculator is actually not even the true value. And in fact, I will argue that you will never be able to get the true value. Even analytically, you'll get the symbolic formula of the true value. But once you punch in numbers, you have to somehow like, how do you compute the exponential or the sine? You have to render it into simpler mathematical formulas with addition and multiplication, and you have to approximate those two. But you approximate them to a very, 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 very high accurate degree, and we say, you know what, that's the truth, that's the true value, okay? So the calculator is giving you a very high quality approximation to the true value using some type of approximation like Taylor series, but we trust that it is the true value because it's a very highly accurate approximation compared to the little approximations that you're doing. So what you just did actually, when you punched the calculator gave you just a very fancy formula compared to the rise over run formula that you used. It could have used a rise over run formula with a very small value of h, much smaller than the values we've used, and claimed that to be the most accurate one, okay? Okay. And so in reality, your calculator expresses all of these complex functions in terms of simpler polynomials. And one of those polynomials comes from the Taylor series, and you've probably seen this in your high school, and that's the classic formula for the exponential function. You see, the e to the power x, we don't know how to compute that. Like, you have to express it in terms of elementary operations, additions and multiplications. And this is the formula here, 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24, and so on. And your calculator keeps adding those numbers until it hits a very, very high accuracy, okay? And we call that the truth, okay? But how does the calculator tell how many terms it needs to give for a reasonable value of e to the 0.3? So your calculator is going to keep adding those terms, and they're all going to be approximating the true value. But how does your calculator tell when to stop? It has to have a mechanism inside it. This is because this is an infinite series, right? It has to have a mechanism in it to say, okay, I'm going to stop here. This is the best I could do, right? So we can try it out. If you take one term in this approximation for the exponential, you get an approximation of e to the 0.3 equal just one term is 1. It's a very bad approximation. If you put two terms, you get 1.3. If you put three terms, you get 1.345. So what I'm doing here, I'm taking that approximation for the exponential, and I'm evaluating e to the 0.3, so x is 0.3 in all of those terms, and I'm going to keep adding terms. I'm going to keep adding terms to it and see what happens. We're just going to explore what's going to happen. Okay, so with one term, you only take the first term in that series. You neglect everything else. With two terms, you take the first two terms. With three terms, you take the first three terms, and so on. And you can keep doing this over and over again. And here's a table of me doing this exercise. And you see with one term, you get 1. With two terms, you get 1.3, 1.345, 1.34495, 498,375, 49857, and 7 terms, 1.3498, and so on. And then something happens. You see, like, after, 11 terms, 11, 12 terms, it doesn't change anymore, right? The answer doesn't change anymore. You're no longer getting any more significant figures, right? So you stop at 7576. There's nothing more. That's the best this calculation could do. So, doing 12 terms in the Taylor series or 20 terms is not going to make a difference, because that's the best answer the calculator could give us. Okay? So here's my question to you. Remember, in this case, I don't know the true value. There's no true value for e to the 0.3. Forget the concept of that true value. But from what you've seen here, can you come up with a way to define an error in my calculation? Can you come up with a way to tell me kind of when to stop? So the calculator inside is doing this, is adding terms, keeps adding terms, until it reaches a certain error, or until it reaches some place where, like, you know what, I'm adding terms, it's not going to make a difference anymore. How can you tell that?
You can just tell the calculator to go to a certain number of decimal places.
How do you tell it that? How does it know the certain number of decimals?
Maybe if you program, let's say, like, to say, if, like, once you, like, for maybe 10 terms, if you have, so if you, anything, like, so if you calculate.
How does it know the true decimal places? Because all of those here, they have the same number of decimal places, right? Okay. So I had another answer. Yeah. Yeah. So when the answers look the same, that's kind of what you see, right? As a human, you look at this and like, it's not changing. The value is not changing anymore, right? So we can stop. Or as your colleague said, more kind of mathematically, if we take the difference between any two successive approximations. So you agree that each one of those is an approximation. This is with 12 terms, this is with 13 terms, this is with 14 terms. If you take the approximation with 14 terms minus the approximation with 13 terms, and if it's less than a certain tolerance or error, 10 to the minus 13, 10 to the minus 5, you're just like, stop. You can't do any better, right? And that's exactly it, okay? So if I take that difference between two successive approximations, this is the error between two successive approximations, every two. So the first one is between 1.3 and 1, the second one 1.345 and 1.3, and so on. Like, this is the error between 12 terms and 11 terms. It's like, what, 10 to the minus 10 or something, right? Can't do any better anymore. After that, it's 0. It cannot do any better. So then we can program in the calculator a mechanism to say, just stop when you reach a certain tolerance. Typically 10 to the minus 10 is quite good tolerance, okay? So that gives us a an idea for how we can define an error when we don't know the true value. Instead of focusing on the true value or whatever, let's focus on this calculator or the machinery that we have on hand, the computer that's running these calculations. Once it reaches, it cannot do any better, that's it. That's the best it could do, and that's going to be our error. We're going to call that our approximate error, okay? So this gives us the concept of an approximate error, which is defined as the difference. Instead of taking a true value minus approximate value, now we're going to take a current approximation minus a previous approximation. But there's a fundamental assumption that I made here that the current approximation must be a higher accuracy one. So think of the Taylor series example. We know, because the Taylor series does converge to the true solution in the limit as the number of terms go to infinity. So it's a convergent series. The more terms I add, the better result I'm going to get. So I know that the approximation with more terms is better than the approximation with less terms. Or the current approximation is better than the previous approximation. Or, in other words, the higher order approximation or the more accurate approximation minus the less accurate approximation. That's another way of saying it. Okay? So typically, a current approximation means a supposedly better approximation than the previous one. So this could be also written as saying better approximation minus or more accurate approximation minus less accurate approximation. That's why the first example we did when we took the value from the calculator minus our, poor man's calculation value worked, because the value from the calculator is a very highly accurate calculation minus our very poorly accurate calculation. Okay, that's why that error kind of worked and was okay. But this is a much more elegant and appropriate approach for actually what happens in all systems that have to do with numerical methods. So here's the other definition. It's the difference between a more accurate approximation and a less accurate one. Okay? So any time you develop a new method, even if you don't have a true value for a system, but you have a method that is more accurate because you proved it already more accurate with some other mechanism, you can use the more accurate method as your truth. Okay? This is a very powerful way of doing this. So with sensors, for example, we typically compare to previously validated sensors where we know that they are more accurate. Like they're more expensive, they have more accuracy in them. We already tested those. We don't have to go through the exercise all over again. We just put two sensors next to each other. One of them is a high quality sensor, a high accuracy sensor. The other one is a low accuracy one, and we use that high accuracy one as our truth. Okay? The same way we defined a relative true error, we can define a relative approximate error. Because the approximate error, again, doesn't tell you how big the error is. So yes, the difference between the two numbers is 10 to the minus 13. But if the number is on the order 10 to the minus 13, then the error is 100%. So you need to base your approximate error also with respect to something. And in the end, this is the only error that's going to matter for us, the relative approximate error. Okay? And the same way we did with the true error, we're going to take a current approximation minus previous approximation over the current approximation. Why we treat the current approximation in the denominator? Because we assume that the current approximation is the more accurate one. It's closer to the truth. So it's like the true value, okay, in the denominator. Equivalently, more accurate approximation minus less accurate one over the more accurate approximation, okay? So that pretty much summarizes the approximate error, the relative approximate error, which is going to be our primary go-to way of calculating errors as we develop new technologies in the course. Okay, so we're going to do an example together. Again, going back to those first derivatives. Okay, and this is going to be we're gonna actually jump to Python eventually with this one, but we're gonna do it by hand first, just to show you how you could operate around these concepts here. So Again, we're going to go back to the first derivative of a function, which is approximated with this formula, rise over run. By the way, this formula is called the forward Euler formula. Why do I mention that? Because Euler is like everywhere, and we're going to come back to this formula when we touch on numerical calculus, okay? So if you don't know about Euler, like you have to read about Euler. He's like the most brilliant mathematician who ever existed. He's one of my big heroes. So derivative, rise over run, and h, again, is some small value. Now we know that the smaller the value of h, I just mentioned that, and we know for a fact from math that the smaller the value of h, the more accurate this approximation is. So that's going to be helpful because that is going to allow us to define how we're going to measure our relative approximate error, what's going to be the more accurate and the less accurate approximation. So we're going to go through this problem again. For f of x equal 2e to the half x, we're going to find the relative approximate error in evaluating f prime of 3, so the same question as before. But now we don't know the true value. We're going to assume we don't know the true value. We want to measure the relative approximate error for h equal 0.5, 0.25, 0.125, and 0.0625. Okay. So we know that the approximation with this value, with 0.25, is better than the one with 0.5. The one with 0.125 is better than the 0.25 and better than 0.5 for sure. And with this value, 0.0625, is going to be a more accurate approximation than this one. So that's very important to recognize. You have to trust these formulas. You have to know that these formulas, with this value, is going to give you a better approximation than this value, etc. So now we have the more accurate and the less accurate one, and we can take their difference together. So here's how I would do this. And I'm outlining a solution plan just to give you an idea of how I would think about it if I were you. I'm not going to do this for every problem. On some problems that are complicated, I'll do this with you. But just to illustrate to you the concept of how I would approach it in a very systematic and simple way. So first, I'll tell myself we're given a formula that approximates the derivative of a function. And this formula depends on a parameter h. The smaller the h, the more accurate the answer. So this is where your insight comes in. You have to recognize that the smaller the value of h, or the more terms you add to the approximation, the more accurate you are. That's going to be the key insight here, okay? Then we are asked to compute the derivative of f of x, 2e to the half x, for all of these values for h, and find the relative approximate error. Now, for each value of h, we can compute the approximation to the derivative. And for each approximation, we're going to compute the approximate error based on the difference between the better approximation and the one just before it. So we're going to take the difference between the derivative computed 0.25 and 0.5, and then 0.125, 0.25, 0.0625, and 0.125. You see how we're going to work this? All right, so let's do this. We start with a table for h, f prime approximate at 3, and our relative approximate error. For the first value of h, 0.5, we get an approximation of 5.09, but we cannot define an approximate error because there's no worse approximation. This is our starting point. So I'm going to leave this blank. As far as I can tell here, it's an undefined error. We don't have any worse approximation than this. Now, when we go to 0.25, we get a better approximation. And now if I take the difference between this and this value and divide by this better approximation, I get a sense of the relative approximate error. You can tell it's 6%. Okay? So we take a smaller value of h, we get a different value for the approximation, and the relative error goes down to 3.22%. And indeed, as expected, even for the approximate error, it should go down. And this is what you see. 6.6%, 3.2%. You take one more h value, 0.0625. You get a different value for the approximation. You take this guy minus that. So better approximation minus worse approximation over the better approximation. And that gives you a relative approximate error. OK, good so far. You have to repeat this by hand at home, because in your work assignment, you're going to repeat something like this. But it's good to do it over a few values. Anchor these concepts in your mind. OK. So now, what do you observe? I want you to observe something here. That's where insight comes in. Okay? What's happening to the error? What's happening to h? So we have two things going on. We're changing h, and the error is changing. How is the error changing with h?
Looking like h is half, the error is also half as well.
Okay. Any answers? More than 50%, you think? I would say it's just about half. I mean, because there's errors involved here. So within an approximation, in general, the trend, it's correct. What your colleague observed is that, OK, so see the trick here. How are we changing h? On purpose, I'm cutting it by half. 0.5 goes 0.25. 0.125 divided by 2.0625. What's happening to the error? 6.6, 3.2, that's about 3.3, and then by half, 1.5, right? It keeps cutting by half. And that is true. Now, there's a reason for that, which we will study later. This is called a first-order approximation. If this h is cut by half, the error is going to be cut by half. We're going to learn about second-order approximations, where you cut h in half, but the error will be cut by a factor of 4. Third-order approximations, you cut it by half, the error is cut by a factor of 8, okay, and so on. But this is a good exercise in like how you develop insight. How did I tie these two in? Because this is the only thing that I'm changing. I'm changing h. Something happens in the middle, and I get an error. How is the error changing with h changing? What matters is, how is h changing? I'm cutting it by half. What's happening to the error is being cut exactly by half. Okay? All right. So we're going to do this in code right now. But before that, let's take a few minutes break. Okay? 3 minutes. 3 minutes is enough. Okay, let's do 3 minutes. Stretch your legs, get some water, and come back. We'll do the programming activity, and we'll call it a day. Okay? Thank you. Yeah, thank you. Thank you.
asking me about the replicating your slides for the
Yeah.
homework. Did you want them to replicate like all of them, like including like the intro slides and like?
Of course not.
Oh, that's what I thought. I was just like,
Yeah.
I was like, there's no way, right? I was like, there's no way.
Yeah. Let's resume. So this one is gonna require Jupyter notebooks. So let's get your Jupyter notebooks up and running, please. Let's get your Jupyter notebooks up and running. So we're gonna repeat the same. We're gonna repeat the same exercise, but now we're gonna do it in Python. And with Python, we're gonna be able to do many more values of h, and then see if actually, as we cut h in half, we actually see the error being cut in half. We won't be able to finish the whole thing today because of limited time. But we're going to do the brute force approach where we're going to use Python as a calculator. And then we will start augmenting our abilities to use Python to hit a point called, using array slicing, which is going to, and vectorization, which is going to solve this problem in just a few lines of code. Okay? So again, this is the same problem. I'm going to put the slide on the side. It's hard to have both the Jupyter Notebook and the slides next to each other. So I'll try to keep it floating, and we get back to it as needed. But this is the same problem. We're going to measure the relative approximate error as a percentage in computing this forward Euler formula for the function e to the half x. So that gives us the derivative for using all of these values of h. We're going to start at 8, go all the way to 0.0625. And we can drive this to any number we want, but this will serve as a good illustration. All right, so let's get our notebooks up and running. So I'm going to create a new notebook here. Let me see. New notebook, Python 3 on my end. And I'm going to move it to Creston. Okay. All right. So for those in the back, I'm going to zoom in until you guys can see. All right, so let's see. That's good? All right, great. Okay, so I'm going to call this, fall 2024, coding activity 2, approximate derivative, relative error. Okay. So I'm going to lead by a bad example here by not putting text here because I don't have time. But in your homework assignment, you are expected, and I want you to put a description of what you're doing. So, start with the first cell, put your name and your unit, whatnot, and convert it to a text cell and say, in this exercise, we will compute, et cetera, et cetera, et cetera. Okay? So put a description of what you're doing. That will actually help you understand what you're doing. Okay? There's a very powerful thing that happens when you write things. It forces you to think about what you're doing. Okay. So the first approach is going to be a brute force approach. But before I do the brute force approach, together in this class, we're going to start building what I call the boilerplate for numerical methods. These are modules and functions that we will use consistently, like NumPy, Matplotlib, etc. So the first thing I do whenever I open a notebook, I get my boilerplate. Either I grab an old notebook where I have the boilerplate already typed up, I copy and paste, or here I'm going to start kind of doing it from scratch with you. So all I need in this case is NumPy. Import NumPy as NP. So if you've done the EasyPy slides, you've already seen this. If not, I'm giving a nickname for the library NumPy, which is going to be our de facto standard for dealing with arrays and crunching numbers in numerical methods. All right. So first, we're going to start with the brute force approach. Okay, the brute force approach, and using Python as a calculator. Python as a calculator. So essentially, Not a good idea. But it gets the job done. If you do it this way, you do it that way, that's your choice. But I'm telling you, that's not going to help you later on because that's not going to be an effective way of using Python. So let me move the slides so that I remember what I'm actually doing here. Position on screen, bottom. OK. So if I move my slides over here, so we're trying to compute the derivative at x equals 3 for a bunch of values of h. OK, and the function 2e to the 0.5x. So the brute force approach, we're going to say x equals 0.3. So we're declaring our value at which we want to compute the derivative. So this is called a comment, so that you understand what you're doing in your code. Okay, and then we're going to do this approximation at h equal 8, h equal 4, and so on and so forth. So let's go ahead and do it for the first value of h equal 8. And I can simply implement my formula, which is f of x plus h minus f of x over h. So I would put 2.0, which is my function, right, times numpy.exponential. That's how you get to the exponential function in numpy. So we're calling the exponential function in NumPy. If this is not clear to you, just copy it as I'm doing here. It will be clear when you do the EasyPy. But I'm accessing the exponential function from the NumPy routine, from the NumPy library, NumPy module. Okay, and I'm going to do x plus h. So that's going to be x plus h. Okay, minus, there's a 0.5. 0.5 times x plus h. Don't forget your parentheses. Okay, minus 2.0 times np.exponential 0.5 times x agreed. Okay, and all of that is going to be divided by h. Correct? So that's f of x plus h minus f of x over h. My f is 2e to the 0.5. So f of x plus h is 2e to the 0.5 times x plus h minus 2e to the 0.5 times x over h. So let's store that in a variable. Remember, we're going to take the difference between this approximate value and some other approximate values to get the approximate error, right? So I'm going to call this, because it's a derivative, I'm going to call it df8. So that means this is the derivative at h equal 8. Okay, and we can print it, print df8 to make sure everything is just giving me a number. Okay, it's giving me a number, good. Good stuff. Okay, great. So now let's go and do it for h equal 4, right? So I'm going to copy and paste this for h equal 4 and apply it for h equal 4. So what I did in the brute force approach, I changed the value of h, and then this calculation still stays the same. It's a different value of h. And I'm going to call this df4 because that's the derivative with h equal 4. So this is the better approximation than this one. And if I take their difference and divide by this one, it's going to give me our first relative error. Okay? So if you think of the slides, that table here, if you think of this table over here, okay, we're doing h equal 8 and then h equal 4, which is going to give me our first error approximation. And so what is the error? We'll call it E1. And it's the absolute value of df4, the better approximation minus the worse approximation over the better approximation times 100. Okay? So it gives me a percentage. Okay? And then I can print, E1 is equal, E1, and then percent. Okay? So our error is 319%. This even makes sense. Hold on. Okay, 300 and so times 100. Okay? That's a pretty high error. Okay? Okay. And now we repeat. We got to go to different values of h. So I'm going to just copy and paste this. Again, this is the brute force approach. Okay? Using Python as a calculator. H equal 2 here. df2, let's call this E2. is going to be df2 minus df4 over df2, and print E2. Okay, so the error now is 85%. It's pretty high, but it's shrinking. It's going down as we lower the value of h. And we can keep going, okay? We can keep going. H equal 1. So that was the other value, right? So in this exercise, we're doing 8, 4, 2, 1, 0.5, and so on. So df at h equal 1. You don't have to change anything here because this over here, x is the same for all of them, but h is being redefined here. So it's a new value of h. It's going to plug in here and give us a correct, an appropriate value. And then we call this whatever, E3, let's say. And that's going to be df1 minus df2 over df1. Again, in my mind here, better approximation minus worse approximation over better approximation. Better approximation minus worse approximation, better approximation, and so on. Okay? Okay. Over df1 times 100, and then print E3. It should again be shrinking. So now 85, 32, and you know, we can repeat that one more time, 0.5, and df 0.5, you know, and E05, let's say, and it's going to be df05 minus df1 over df05, and that's going to be E. Actually, let me call it E4. That's so confusing. Okay, E4 is now 14%. So now we're starting to see the cutting in half pattern. Okay. Okay. I'm going to stop here because like this is giving me like anxiety now because like this is a terrible way of doing this. Okay. Why is terrible way? Because we have that same formula. This here is the same. This here is the same. The only thing that's changing is h. Like, why do we keep copying and pasting and copying and pasting? I mean, this is coding, for goodness sake, right? This is not like a calculator. So it's a terrible use of Python. You can do it this way. Again, you know, I'm not going to judge you on that. But that's not the appropriate way of using a powerful tool like Python, a coding platform. Okay? And still, if you want to do it this way, what if I give you in your homework assignment to do this for 1,000 values of h? 8, 7.95, 7.9, 7.85, and all the way to 10 to the minus 4. Are you going to copy and paste this 1,000 times? Right? That's, you know, that gets usually the point. You know, you can use this approach for like little quick calculations, but in practice, that's not an effective use of Python. So we're going to do this. We're going to elevate this. We don't have time today, unfortunately, but on Thursday, after the exam, we're going to pick up from here, and we're going to take this and start making it better. We will do it. You might tell me, you're going to tell me, oh, let's do a for loop. Okay, great. There's an even faster way and better way than a for loop, okay? So we're going to augment this. We'll do a for loop together, and we'll do the slicing together, and we'll see the best way of doing this problem, okay? Thank you, and good luck for Thursday, okay? Yeah. Okay, 1 second. Let me stop the recording.